So let's talk about getting our hands dirty and running some simulations on OpenPiton. I'll be talking about simulating using OpenPiton RTL. First, before we start any simulations, let's break down what the anatomy of a simulation is. The simulation is basically composed of two parts. You have your simulation model and the test stimuli. The simulation model has the design that you're testing, the RTL for the design that you're testing, as well as the top-level test bench that contains that design under test, as well as some simulator or compiler arguments that you want for this particular test, such as Verilog macros, any files you want to include, or params or things like that. For the test stimuli, we support a variety of different tests. So today we'll be doing mostly assembly tests and C tests. But if you want, you can get to the low-level bit vectors of input and output bits based on the infrastructure at Cornell by Chris Batten's group. OpenPiton supports many different simulation models. Each of these is either a component of the overall OpenPiton design, or as we'll be focusing on today, the Manycore simulation model is a parameterizable Manycore full system. Each different simulation model allows you to run different tests on them. The smaller subcomponents really only have unit tests that you can run on them, but this Manycore model that we'll be working with today has support for higher level tests such as C and assembly. To run these simulations, we're going to be using primarily one tool, SIMS. SIMS is found in the Piton tools source subdirectory, and this is adapted from the OpenSpark T1 code. With SIMS, you can build individual simulation models and run individual test stimuli. We're also able to, for a particular simulation model, run regressions of tests on one particular model. SIMS supports many different simulators, as we've mentioned earlier in this presentation. We currently support Synopsys VCS, Model Sim, and today we'll be using Verilator. Content, in contrast to SIMS, it calls SIMS and is really used for more continuous integration. Our group uses it. We run tens of tests every night on our entire code base to make sure that all the development work we're doing doesn't break anything. Content makes repeated calls to SIMS with continuous integration bundles. So SIMS is only allowed to, or is only able to build one simulation model. What Content can do is build multiple simulation models and run multiple tests on those various simulation models. Currently, Content only supports the Slurm job scheduler and VCS for simulation, but it should be not too hard to integrate it to whatever system you have. As I previously mentioned, we've got a lot of simulator choice available with OpenPiton. We support many different types. So we've got VCS, Model Sim, and Verilator. And if you want to only focus on the Spark core and not use the Ariane RISC-V core, we also have support for Cadence Incisive and Icarus Verilog. In this presentation today, and you'll be seeing commands that are used for Verilator because that's the simulator we're using today. But if you want to use a different simulator, it should be fairly straightforward to just cut and paste, replace anytime you see VLT in these slides today, replace that with VCS and you can run it for VCS. Or if you want to run Model Sim, just change the flags from VLT to MSM and it should be good to go. So building a simulation model, there's a couple of components that are required for a simulation model. We're going to call SIMS, and we have two required components. We have the definition of the simulation model, which today for us will be Manycore, and a flag indicating that we are building a simulation model. You can have other useful arguments if you want any particular arguments to be input to Verilator, or if you're running a simulation using VCS and you want a more graphical interface, you can use the debug all flag so that you can view the waveforms later interactively when running your simulation. The simulation, when you build a simulation model, there's a large stream of text going out to your standard out, and all of this is also output to a file called sims.log, so you can search through that to debug what's going on when building a particular simulation model. If successful, your simulation model should appear in the build directory under build, the name of the simulation model, and the build ID. You can define this build ID as a flag when calling sims, so this is another useful flag to use. By default, however, we see that the build ID is going to be release 0.1. So we'll see that later today. So for example, if we were to build a Manycore model of a couple of cores put together, we could call sims, indicate that we want to build the Manycore simulation model with the flag VLT build, and a flag called for Ariane to indicate we want to build an Ariane core. This will then cause the Manycore model to be built, and we can check the sims.log file for errors. The keyword you want to look for when debugging is a sigdi. If you see a sigdi in your sims.log, chances are something went wrong, and that'll be the first place to look for when figuring out what went wrong. And the resulting simulation model will be output to build Manycore release 0.1. So we can do this right now, get our hands dirty, and start building a Manycore model. So if you all go to the Piton root directory and have already sourced the Ariane setup.sh, you can move on into your build directory and call sys equals Manycore VLT build Ariane, and that should build a single Ariane core for you. So when this script is finished, you can check your sims.log file to check for build errors. Again, you're looking for that sigdi command, but if you don't see any of that, it means it built successfully. And if you want to double check that the build went well, you can go to build Manycore release 0.1 object directory, and you'll see the chip multiprocessor top file. While we're finishing this up, I'm going to start talking about, now that we've built a simulation model, how do we actually run a simulation? So much like building a simulation model, running a simulation is another call to sims. In this case, you're still going to indicate what simulation model you're going to use with the sys flag, and this time the command is VLT run to indicate you're going to run a simulation. The last thing that's required is the test stimuli, what input you're going to use for the test. This particular test stimuli depends on what type of test you want to run. It could be an assembly file, it could be a set of source sync vectors of bits, but we will see that in a second. Some other useful arguments, if you had written a particular build ID when building a simulation model and you don't want to just use the default release 0.1, or if you want to make different builds of the same simulation model, you can identify which build you want to run the simulation on using the build ID flag. And if you built your simulation model using the debug all flag, like I mentioned before, and you're using VCS or ModelSim, using the GUI flag will open that simulator and let you do an interactive waveform viewing while running the simulation. So the simulation outputs quite a bit of things. It depends particularly on the test type. So when you run the simulation, you're going to see, again, another large deluge of information on your standard out, which also gets output to your sims.log file. And really what we're looking for when running a simulation is near the bottom, not exactly at the bottom, but near the bottom of your sims.log file or on your standard out, you should see a line that says pass, hit good, trap. Our tests are built such that when all the checks are in place, it hits a good trap and goes to a particular location of memory. And if we see that, then the test passes. You'll also see the test binary, so your assembly or C program is going to be compiled into a binary, which will be named diag.exe, and you'll also see a bunch of other information related to the simulation, such as the image of memory at the time, a symbol table, performance log, and status log. You can look through all these to find out more information about how the simulation went. So here's an example. Don't type this quite yet, because there's another step to add, but if you want to run a C program, we've got a simple Hello World C program that we can run. As I said before, it's a call to sims, indicating we want to use our Manycore system model with a VLT run, and indicating that we want to run on an Ariane core, indicating also that we want to run hello world.c. Other RISC-V assembly tests that we have released with OpenPiton have generally the same syntax as this C simulation does, but the input files end with .s or .RISC-V. So now we can get hands-on. If you go back to your build directory, make this call to sims. It's basically what was on the previous slide, but we need to up the RTL timeout count to 1 million so that you get enough cycles in before the simulation times out. So when this simulation runs, it'll take a while to run this particular simulation, but you should look at your sims.log after the simulation completes, and near the bottom you should see the pass hit good trap at the end. And also there will be an output fake uart.log, which should be the output of the hello world script. So yeah, enter this command. Let's run our first OpenPiton simulation, and if you have any questions or problems, raise your hand. But yeah, you'll be seeing a bunch of output like this. So while this is running, I guess I can explain what is appearing on your screens. There's a whole bunch of output here. The thing we're looking for is pass, hit good trap, near the bottom, not exactly at the bottom. If you see that, test passed, and woohoo, you did it. So in a couple slides, I'm going to go into more detail about all the information that's above this. First, let's talk about debugging your simulations. So there are a couple levels of debugging you can do. First, at a higher level, you can have monitors for the Manycore simulation model. These are non-synthesizable Verilog modules, which keep track of different performance counters of interest. They're instantiated on the top level test bench and use cross-module references to pick up the individual signals of interest that we want to keep track of. These monitors print out useful output, as we'll go into a bit, to basically give you snapshots of what's going on during the simulation. They can be useful to either track values over time, but they can also check if certain properties are met at any point in time during the simulation. So if you see this information on your screen is way too much and you want to have a more minimal simulation, if you add the flag to your sims command config RTL equals minimal monitoring, you'll have less of a text flow. But there are also some tools available to help look through that to get more useful information as a digest. But let's look at that text. So this screen has quite a bit of information on it. First, I guess near the top, we can see this is a snapshot of what the pipeline looks like in one of the cores. We can see instructions going down the pipeline. We also have information about when the PC is updated. It tells you specifically what thread on which core gets updated and which value it gets set to. So you can track the PC of a program on all your different cores of your Manycore model and see how they change over time. You also can track the registers within your simulation, which registers are updated when and what values they're updated with. There are messages relating to the memory system. You can see memory requests going out and what the different components of those messages are, what they're requesting, who they're requesting from, what the data is, things like that. As well as some information about the on-chip networks and the messages that are being passed back and forth between your multiple cores. As I mentioned before, if you want more low-level debugging and these monitors are too high-level for you, you can look at individual waveforms and see the ones and zeros. You can get the graphical interface using the debug all and GUI flags when building and running your simulation respectively. And that will bring up a graphical interface using DVE. And at which point you can find your chip, find the module within the chip that you're interested in looking at, and add those waves to your waveform viewer, and see and track the changes in the values as time goes on. When you add these to your waveform viewer, in DVE in particular, you need to add them to the waveform viewer first, and then click the Run Simulation button in the top left to start actually running the simulation. At which point you can pause at any time, go back and forth, step through the simulation if you want to see the behavior of your chip as time goes on. You can also do graphical debugging with ModelSim. Very similar. If you run with the GUI flag and log all, as shown in this example, it'll open up a very similar looking graphical interface, in which case you can add your waveforms to the viewer and do a very similar debugging process. All right, so how's everybody's tests gone? Have we succeeded? Passed? Passed? All right, fantastic. So now that we passed our first test, we can talk about more of the tests that we have included in our assembly test suite with OpenPiton. So a lot of your assembly tests are going to be found in the Piton Verif diag assembly directory. These are composed of diag lists. So any file ending in .diag list is a list of tests that we have that go well together. The group of assembly tests and the declarations of the assembly tests themselves. So the base component of a diag list is an assembly test declaration. This is composed of a label for that assembly test, the input file for that test, as well as any particular arguments for that test. And these assembly tests can be grouped together using an XML-based form. You can indicate a group of assembly tests that you want to run as a group, give them a group name, the one simulation model that they all execute under, as well as some common sims arguments to all of those tests. And much like, or within an assembly group, you have individual assembly test declarations. So here we see the group is called group name, and we have test1 which runs test1.s. Something that can be really useful for your testing purposes is that groups can be nested. So if you want to have a more hierarchical grouping of your tests, you can use assembly groups pretty effectively for that. So here's an example of a diag list. Here we have the Princeton test, which runs the Princeton test.s assembly file, and with specific flags for that particular simulation. You can also see that we have the Princeton test assembly group, which runs the Princeton test, basic IO test, and hello world test together as a group. So some common test flags that you may want to use, RTL timeout. So we just use this in the hello world.c. This indicates a certain number of cycles you want to simulate before timing out of the simulation. If you want to specify any particular arguments for the Verilog simulator of choice, you can use the simrun args flag. We can indicate to Midas any particular flags. Midas is a Spark assembler that if you're using the base OpenPiton without Ariane on the Spark cores, you can pass arguments to Midas that way. And also, if you're running a multi-core simulation or multi-threaded simulation, you can use the finish mask flag to indicate which threads you're waiting on to complete before the entire simulation finishes. So here's an example of some using precompiled tests. So we also release some precompiled RISC-V tests with OpenPiton. And so if you want to run basically, let's say up top here is a basic assembly test which tests the add I instruction. You can do a call to sims with all the usual flags that we've been using today, indicate the assembly test you want to run, and then add the precompiled flag, which indicates that this assembly program has already been precompiled, so that you don't try and compile it again. So if you want to run that, you probably can. It'll only take a couple of seconds, I think. But not only assembly tests can you run through this method, you can also run larger benchmarks. So we have some RISC-V benchmarks, like the drystone.risc-V, which will take a little bit longer to run, but still good examples to work through if you wanted to. So as I mentioned previously, you can use sims to run regressions of tests. These are groups of tests defined together as in a diag list. Regressions require the use of one simulation model. So you build one model and run many tests on it. If you want to run a regression, it's a different way to command sims. Basically, you can say sims, and then using the sim type flag, indicate what simulator you want to use, and then indicate which regression group you want to use. This is basically the same thing as doing the build and run commands for these tests and for this one particular simulation model. So here's a bunch of different examples of regressions that you can run using OpenPiton. We have lots of different assembly tests, different benchmarks. For one core, we have one core, we have 16 core, we have one tile, different groups of simulation for different system configurations that you want to run. Regression outputs. So they're going to be output to the build directory. And when running a regression, these simulations run one after the other sequentially. And they're all output to quite a large number of files. So if you want to check the results, you can check the test results directory, which is in build simulation model build ID / the date and time or date and ID of that particular regression. And if you use the reg report command on that output directory, it'll show you a synthesized summary of results. So here on this regression output, we can see 46 tests have passed, 0 have failed. Yeah. And then below that, there is slightly more detailed information about if a test had failed, why it had failed, and things like that. So in addition to regressions, we have continuous integration bundles. These are more used for larger scale tests or testing many different components or configurations of your design. So this supports multiple simulation models and as specified in an XML format. So here we can see a continuous integration bundle. It contains, let's see, we have the bundle and the name of that particular bundle, as well as individual assembly regression declarations. And so up top here, we have an assembly test for a particular assembly test, which indicates which simulation model that test does, as well as the diag for that test. You can also have regressions of tests, which have a particular simulation model, as well as the name of the regression group as before. These are also hierarchical, so you can nest continuous integration bundles within one another for further ease of development. So we have a lot of continuous integration bundles already in use with OpenPiton. Every time we push to our repo, we run certain tests. Every night we run even more thorough tests. And we also have more specific tests for different configurations of 2x2, 4x4, 6x6 tile systems. So to run a content bundle, this is going to be another tool we can use. So content is a continuous integration tool. which currently, as I said before, supports Slurm, the Slurm job schedule in VCS simulator. To call it, you will call content and then indicate which continuous integration bundle you want to run. So for example, if you wanted to run the tests, all of the tests that we run whenever we push to our repo, you can explicitly call content with the bundle get push. And that'll run a bunch of, for us, quick tests to make sure that nothing major has gone wrong. The content, much like all the other simulations, has a bunch of outputs. So the results will be aggregated and printed out to standard out. Again, each of these individual simulations will have output files in your build directory. The naming is a little bit different. It'll be under the build directory, it'll say content and then some identifying numbers about the build and the date and things like that. So much like a regression, you don't necessarily want to go into each individual test to see what the results are, so you can reprocess the results by calling content again, using the check results flag at the end there to basically create another summary of results. So here below we have an example of this. So on this continuous integration bundle that we just called in the previous slide, you would call content again with that bundle with the check results flag and pointing to the output directory of that continuous integration run, and you will see an output file like this. This shows us all sorts of information about what tests passed, which ones failed, either in building or in running. And if they failed, as you can see here, we've got 2,197 tests passing, but 3 failing, and 7 unfinished. So in this report, you can look at the high-level results, and then right below those high-level results, you can see why these particular tests failed. So we have one hitting a bad trap in the top, and then we have one down here at the bottom, which was more of a timeout, and give you more information of why these tests went wrong, so you can start your debugging process with a little bit of information.